Good morning, I'm Jean-Louis Van Bella. I did a few videos on YouTube already on quantum mechanics. Um, this is going to be one on particle reactions. Unstable particles, they decay, and how does that work actually, and how does it being described in in quantum mechanics. I'm not going to make any compromises here. This is very technical and very advanced notation and all that. And I'm going to be short. I'm just going to go over it. The full details of this, of what I'm going to talk about, are in my last paper, or one of my last papers on ontology and physics. You find the reference there on the research gate, and I'm basically going to explain the annexes to that paper because they have that all that technical stuff. So basically, quantum mechanics, you have I'd say you have like two quantum mechanics, the new one and the old ones. The new ones developed sort of in the 70s, 80s, and analyzes unstable particles in terms of quarks, as a quark hypothesis. I call it a hypothesis because for me, quarks are more like mathematical entities. So then you have all that stuff around, the confinement hypothesis and this and that. But sort of that's an analysis of, we're going to be talking about K mesons or kaons. They're charged kaons, plus minus. We're going to talk about the neutral kaon in a minute. But they analyze sort of the decay of that very short-lived particle. We're talking, billions of seconds here. Into a pion, and a pion decays in a meson or an electron or a positron. Depending on the charge. But here you sort of see the new analysis, which analyzes that as sort of quarks, being created out of some quarks that were there with interactions, weak interactions, strong interactions, and then intermediate bosons, vector bosons, W particles, and then the gluons. We basically think that's a very flawed and difficult and very approximative actually description of what actually happens. So where did it all start? I put those two illustrations there. They come from Feynman's lectures. That's basically how they first looked at these things. Basically, cosmic rays, when they enter into the atmosphere, they consist of particles. When they create new particles, and this sort of a whole flux of it, and they decay. And so in a cloud chamber, as they call it, you can actually see that happen. They will take pictures of what happens by sort of changing the pressure slightly, and subcritical pressure. These chambers are under subcritical pressure, and then sort of you can see these reactions taking place as little bubbles. Charged particles will usually be magnetic fields. So charged particles or an electric field will have curved trajectories, and you can see these. If there's no electromagnetic field, then they just go in a straight line, as we see here. So basically, the zoo of particles that you have there. So a neutral kaon decays into a positive plus pion and a negative pion. There's all kinds of other intermediate particles. There's lambda particle there on the right hand side, where you have the antimatter counterpart of a kaon interacting with a proton to produce a neutral lambda particle, plus again a positive pion, and that sort of then further decays into the negative and the positive pion and the proton that we started out with, but which has different energy, kinetic energy. So you can see these are all what they refer to as high energy events. And the question that puzzled the researchers at the time was basically, a neutral kaon has certain reactions, decay reactions, and its antimatter counterpart as well, as we can see in the illustration. But there's sort of a number of reactions that do not take place. And people were very puzzled about that. So for instance, one that Feynman focuses on in his analysis is this one. If we would have just a normal, just normal matter kaon interacting with a proton, why don't we see that reaction? The same thing, a lambda and a positive pion. It conserves charge, it conserves energy, it conserves momentum, it conserves angular momentum, all these kind of things. But this reaction doesn't happen. The key, of course, is in what is an antimatter particle. These kaons are actually composite particles. What goes in must come out, and they're neutral because they actually consist of two charges, and it's like a neutron that we analyzed in previous presentations. There's a positive charge and a negative charge, and we can see them, and sort of the nuclear force will keep them together, while the electromagnetic force will push them apart. But so in the end, they're in an orbit. The thing though is with these kaons and with neutrons as well. We shouldn't be thinking of these positive and negative charges as an electron and a positron. No, there is a charge that is like proton-like, quite massive. That's sort of an oscillation of itself, and a much lighter electron-like charge, as I would call it. And so that explains actually why antimatter particles. It's just a matter of reversing the charge, minus and plus. You should look at the nature of the orbits these charges are in. So that's why a neutron and an anti-neutron and a kaon and an anti-kaon are quite different. I talked about antimatter before, and you could find it in the papers. The basic analysis is that yes, they have opposite charge, but they also have an opposite space-time metric. A positron with spin in this direction, and resembles an electron with spin in the same direction, but still it has a different space-time signature. So that's what we're looking at, sort of these unstable particles. Unstable particles are described by a wave function. We think of them as an oscillation as well, but it's not a stable oscillation. It's not a harmonic. There's a friction term. They die out, and that's what I put there in the on the bottom on the left hand side. The oscillation dies out, and so to model that, there's basically two parameters you can use, an alpha and a beta, and we will talk about it in the next slide. But so that's basically the question. Why don't we see these not happen? We won't dig into it because we just think, yeah, antimatter is antimatter, and it has different decay reactions. Especially neutral composite particles have very different decay reactions. So here we have these wave functions. I said you can model. I take the U for an unstable particle, so the psi, or the wave function of an unstable particle. We can write it as coefficient a times complex exponential, but in the complex exponential we'll have that alpha and the beta, and you can write that all out, but basically you get a mathematical form that is a transient, as we call it, dies out. And so a transient is basically the product of a stable wave function, one that doesn't die out, the a times the complex exponential with the alpha in it. And so that will be related, both the coefficient, the amplitude A, as that alpha parameter to the energy of the initial energy, because when the particle decays, oscillation gets less, the amplitudes get less, and that's what that other factor is there, the real exponential, Euler's number, when the exponent minus beta t, and that's an exponential decay function. Basically, the mean lifetime of that particle will be given by that beta parameter. And so the mean lifetime is just, well, that's math. When you do complex exponential, the oscillation will have died out by 2/3 after the mean lifetime. So the mean lifetime is the inverse of that beta parameter. We're talking order of magnitude. So as I said, these are very short-lived particles of 10 to the power minus 9 or minus 12 seconds. So very, very short-lived. Still, if we have a stable particle, for the beta parameter there is going to be 0. That's what we model there, and we can just write that as a stable function. I write it out with an e minus beta t and an e beta t, but we basically have that wave function. And I said the energy, the frequency of that oscillation is going to be given by the energy of that stable particle. So for an electron, for instance, you get a fantastic frequency. of the order of 10 to the power 20. That's the frequency, and then the mean lifetime is going to be, infinity, because beta is 0, and so 1 over 0 is infinity. So you can see the alpha and beta parameters generally will have that kind of difference in their order of magnitude, 10 to the power 10. So one 10 to the power minus 9, 10 to the power minus 12, and the other electrons. Electrons are actually quite are not very massive. Proton has much higher frequencies, much more massive, higher energy, higher frequencies. So, but that's sort of the order of magnitude. So that shows, while transient resonant particles do not last very long, we can only sort of see them on these in these bubble chambers, cloud chambers, and um, we measure their lifetime from the distance they travel and then their velocity. But they still pack a lot of cycles, a lot of oscillations during that very short lifetime. In the graph below, I should have show the real part and the imaginary part. We know the imaginary part is not any less real. It's just lags behind the real part. You can think these oscillations, nuclear or electromagnetic. Think of an electromagnetic oscillation. For an electron, for instance, you'll have the real part will correspond to the electric field vector, and the magnetic field vector will be the imaginary part. And so it lags, introduces a little asymmetry because it lags, it's orthogonal and it lags by 90 degrees, or you could say it is 270 degrees in advance, but 90, 270 degrees in advance or 90 degrees ahead. It's not 180 degrees lagging behind. So that introduces small asymmetry, and that sort of also ties into that difference between matter and antimatter. It's not just a matter of reversing spin. This sort of imaginary part basically models, the relativistic aspect of what's going on there, and yeah, it's not just a reversal of spin. So how do we go about that then to sort of model that? I mean, in the old quantum mechanics, and I think that's the valid quantum mechanics, they didn't think about quarks and gluons and all that kind of stuff. No, they basically said we have particles going in, the anti-matter counterpart of the neutral kaon, k over bar 0, and then a proton. You see that in the middle there. So these are the two particles going in. That's the phi state. And then we have a scattering matrix. Particles scatter out, and what scatters out is a lambda particle and a positive pion, p meson. And in between, we have we have a matrix, and sort of that's the scattering matrix, and that's sort of the explanation of what happens. That sort of models that event, that particle decay. So I use here, you will know that this is the bracket notation of Dirac. It's supposed to be read from right to left, like in Arab or in Hebrew, but I don't see the use for that. I think we can just read it from left to right. Physicists will cry wolf and say, "Whoa, no," because certain reactions are not reversible. We think that's got to do with sort of that misunderstanding about the nature of antimatter and the nature of time. Also, actually, it goes in one direction only. So yeah, these reactions are basically reversible. CPT symmetry, if you've heard of that, if you reverse the charges, you reverse time formality, take the antimatter particles, and then the time c and the mirror symmetry, left and right handed side. If you inverse everything, then the reaction is reversible. It's possible. You of course can have individual breaking of CP symmetry and T symmetry, but the combined CPT symmetry should always hold, and that's what's modeled by taking that complex conjugate of that expression there, phi, the operator S, and then the end state psi. If we take the complex conjugate, then we have that thing in reverse order, and basically the S or the A matrix, we have to take the the Hermitian conjugate of that. So what is that expression actually? What does it give to us? It gives us a probability. So it's a wave function itself. We multiply. We're going to represent these particles by wave functions. These coefficients are complex exponentials, are wave functions, and we get a final product that are also described by wave functions. So the whole expression actually, that one is gonna be a probability. If we are considering only this reaction, looking at this reaction only, then that probability is going to be 1. It happens. This thing has happened. Or if we're looking at sort of multiple ways in which these particles can, decay or interact with each other, then we have multiple probabilities. We'll always have some major modes of decay and then some very, very minor ones. So that's it basically. So I write it all out. So that whole expression. So we have, I said I'm doing the normal matrix algebra. That's the reason why I sort of want to stick to right to left reading of that bracket notation. So we have a vector in the phi state. This is the k over bar 0 particle and the proton, and then we multiply that with that matrix, and we get that the particles out. And so we can write it as a system of 2 equations. And I said all these equations are going to be, all the coefficients in them and the particles themselves are going to be described by wave functions. So, and that's what I do below. I write those 2 equations out. So I replace k over bar 0 by a wave function, the amplitude of the k over bar 0 particle, times the complex wave function with an alpha and a beta parameter, which is specific to the k0, the k over bar 0, and then multiplied by S11, and then the other coefficient there, and then the wave function at the end should be equal to the wave function of that lambda particle, which has also its own amplitude, which depends on the energy, and then its own alpha and beta parameters that sort of we get experimentally from the decay times of the and the energy of the lambda particle. So that's it. You'll say the system is not fully determined, and that's why we have we need to combine this with reversibility. We need to look at other decay reactions as well, model them as well. Can the system be determined? Not so sure, because here we really have indeed 4 coefficients: S11, S21, S12, and S22. But there are all kinds of constraints on the matrix, and these constraints are really the conservation laws of energy, of linear momentum, angular momentum, charge. There's really no need to sort of invoke, strangeness, if you sort of make sure that you model antimatter, you understand antimatter correctly. So that's it. That's it for today. I would recommend to read my papers, and well, if you have questions on this or sort of things that aren't clear, or you would note logical errors, don't hesitate to write me. I usually write back, unless you write total nonsense. But that's it. I wish you a very nice and pleasant day.